Good afternoon. This is our second Minerva distinguished lecture series. Typically, in the last 10 years, we have one for each year. Because of the pandemic, we accumulated a few of them to become two. This is very unusual. As I said the last time, it's very lucky, very fortunate for Princeton Maths Department to have this lecture series with financial support from Minerva Foundation. And 10 years ago, I was the first lecture given by J.P. Sayre, and it has been proved a great success. And the idea of this series bring out the best mathematicians in the world to give a serious lecture. And today we are very fortunate to have Wei Zhang from MIT. And Wei was a student from Columbia. And after PhD, he became a postdoc at Harvard and a BP too. Then back to Columbia. Now is a full professor at MIT. And I forget how many awards he received. Okay, maybe it is Ramanujan Prize, Clay Fellowship, and New Horizon, right? I guess, probably many will for the future. Anyway, we have great pleasure to have Wei give this lecture.
Thank you, Zhou, for the introduction, and it's a pleasure and an honor to give the Minerva lecture, and it's also a pleasure to be back here. I think I gave a talk right before the pandemic, 2019, so it's definitely very happy to come again. So today I want to talk about rational points on intersection of quadrics. So actually let me see, is this big enough? I'm not so sure. But we start with sort of one quadric. So we move to intersection of two, or maybe even more. So I wonder if this is big enough or bigger room. It's good. Okay. So so let me start with so let's say I have a n by n matrices with a rational entry, so Aij belong to rational numbers. So the question we are interested, let's say we have a non-degeneracy condition determined in non-zero. The question we want to consider is right. So let's consider the following Drinfeld equation. So suppose I want to solve for x being x1, xn. So we write as x for the vector with n variables. So look at the quadratic equation defined by x times a, so symmetric. So a equal to a transpose. So that's the equation we want to look at, and we want to consider, of course, the solution being non-zero. So the question is, does this equation have non-trivial solutions, namely not simultaneously zero for all the coordinates? So the results proved by, we knew already for more than 100 years, Hasse, Minkowski, which says following. I can even assume the entries are integers by just multiplying the common denominator, since this is a homogeneous equation, so that doesn't hurt. So Hasse Minkowski proved the following result. says that this equation is called, say, star. Star has a solution. I'm writing smaller. has a solution. In Q, precisely when the equation has a solution modular all integers, so only if, so if I consider the congruence equation modulo a prime power has a solution, for all p, for all power of prime p, and also there should be a point. The equation should have non-trivial solution over real number. And also, yeah. Right. So, has a real solution. So clearly one implication is trivial, so the interesting implication is the converse. Suppose we have a solution for all the power of a prime and also real solution, then you can actually deduce the existence of solution in the rationals. So we're going to call, actually this right-hand side, let's just give a name. It's called the local. The right-hand side, let's call the locally solvable. At all primes. So let's just call locally solvable. So left-hand side, we call it globally solvable. So Hasse-Minkowski proved that they're actually equivalent for quadratic for one quadratic equation. So the significance of this implication is that the right-hand side, the local solvability is actually is very much computable in the sense, well, maybe the word is decidable. Decidable in the sense there is an algorithm, so you can design an algorithm. You can let computer to compute. If you input the coefficients, there's an algorithm which will tell you in finite time whether this condition is satisfied or not. So, so in fact, for large primes, you don't have to check anything by Wei's conjecture on points on finite fields. You can always find, there's always a solution with prime p large enough for modulo p. So then you have to do is to lift the solution using Hensel lemma or a version of implicit function theorem. So you get for free for large primes. So that leaves only finite primes for small primes, where you can, for each of them, you can check with infinite time whether the local solvability holds or not. So we're going to call, whenever we have a equation or a system of equations, so which they define certain varieties, defined by such equation or system of equations, if this implication, and clearly one side is true all the time, if this is true, we call Hasse principle. It's called Hasse principle. Holds for this variety. So for simplicity, let's call it HP. So in other words, Hasse principle holds for one quadrics. So here I only stated a result for rational numbers. What happened is it's also true for if you replace Q by, replace this by any number field or any finite extension of Q. So those are finite extension of Q, or also same is true for function field. Of a curve over finite fields. So in other words, finite extension of one variable function field over a finite field. So we will write called K here. Both will be called K. So it's true if you replace rational numbers by those. So in the case of a function field, which will actually be the focus of this talk later on, one can consider, for example, in this case, you can consider the analog of integers being the polynomial ring in one variable over a finite field. You can consider irreducible polynomials. Those will be analog of prime numbers. You can consider reduction modulo irreducible polynomials or higher and higher power of irreducible polynomials. And we ask the same question. Right, so that's for one quadric. So now let me actually, so this is well understood. So we'll now move to intersection of two quadrics. So the Hasse principle actually fails when you move to two quadrics. Let me start with the case when the dimension of the intersection is 1, so the minimal case. So this case, Hasse principle actually doesn't hold. So let me recall one example or counterexample due to Lin in 1940. So if you consider the following intersection of two quadrics, so I'm going to write down two equations. Let's see. So the variable will be called x, y, z, and a w. 2y squared is equal to w squared plus or minus 17 x squared, z squared. So I have four variables, x, y, z, w. So I'm defining something in P3 with two quadratic equations, so that you can check this actually it's a smooth complete intersection. The resulting curve, resulting one-dimensional. So it's a curve, and this doesn't satisfy Hasse principle. In other words, it's locally solvable, but does not have a global solution. So in fact, I can write in a little bit more simple way. I can write the affine equation. So I can kind of assume w doesn't vanish, so replace w by 1, and write a affine equation. You end up with, so I can write it. So there is a so if you clear you plug in z equal to x squared, so you get 2y squared equal to 1 minus 17 x to the 4th power. So that's okay. This has a singularity at infinity, but anyway, it's birational to this curve. In fact, this is a hyperelliptic curve which has a so c goes to P1. So if you sense x, y, x, it's a ramified covariant with 4 ramified points. So this actually gives one genus 1 curve. So G of C 1, which is a counterexample to Hasse's principle. So a natural question is, well, since the Hasse's principle doesn't hold, maybe can we, or how badly Hasse's principle failed for genus 1 curve. So the idea is to, maybe we can group those genus 1 curve, which does not satisfy Hasse's principle into certain common objects. In this case, one can group them according to their so-called Jacobian variety. So the Jacobian variety for the curve, write as Jacobian C. So, in fact, one can even explicitly write down what is the equation for the Jacobian variety. So recall that Jacobian varieties, well, so even at the time of the 1950, this was before the sort of functor language. So Wei already studied such a variety, and he discovered that even in one article he wrote in 1950, that about 100 years before that, Hermite already found a way of writing down what is the equation for the Jacobian variety for genus 1 curve. So in this case, if in fact this works for general hyperelliptical curve of that form, in other words, suppose I have equation given by a degree 4 polynomial, where G degree 4 with rational coefficient, so Q. You can produce its Jacobian variety, its equation by using, so let me write Jacobian. In this case, it's given by the following equation. So y squared equal to, well, I'm writing the affine equation. You can homogeneize to get an equation in the projective space. In this case, where F is the so-called cubic resolvent, so it's a degree 3 polynomial. If you write down, it can be defined in the following way. Suppose this has a root. Well, this works at least if G has leading coefficient 1. So suppose I have 4 roots. So write down the 4 roots. So xi, x1 to x4. So you can produce a cubic polynomial by considering the 3 roots by grouping the 4 into pairs. So 3 roots with x1, x2. So it's something we do in the Galois theory. If you want to compute the Galois group of a degree 4 polynomial, you try to compute this cubic resolvent. So you produce, so those are all possible. We'll group into 2 pairs. So exactly 3 ways. So if you construct this polynomial, cubic polynomial, with 3 roots given by those pairs, that precisely give you the equation for the Jacobian variety. So although Wei actually wrote a paper maybe like 10 or 20 years later claiming that, in fact, this equation not only, this process was not only known by Hermite, was actually even known even another 100 years before that by Euler. So people knew actually how to start with this degree 4 polynomial and produce the Jacobian variety. In this case, it's what we call elliptic curve. So this is, it has a distinguished point at infinity, and it has a group structure, parametrizing degree 0 divisors up to suitable equivalence relation on the genus 1 curve. So going back to Hasse principle, so I can group those genus 1 curve according to their Jacobian variety. So I can consider all genus 1 curve C, and then consider the identification of its Jacobian variety. So with a given cubic equation, cubic curve defined in such a way, where E, suppose E is given, as I mentioned earlier, local solvability is decidable. You can consider it's very easy to do. So therefore, maybe let's assume C is locally solvable. So locally solvable. So let's group all those genus 1 curve with the same Jacobian variety. So maybe slightly more, we're doing slightly more because I'm also including this identification into the data here, but there are only at most 2 or 4 ways, or finitely many ways, to identify those two. So essentially, we're grouping those genus 1 curve with the same Jacobian variety. So this we're going to give a name. Well, for the moment, it's a set. So this is going to be called the Tate-Shafarevich group. For the given Jacobian variety. This was, well, I'm defining as a set, as up to equivalence class, of course. So, it actually has a group structure. It's an abelian group. It has an abelian group structure. It's actually torsion. Torsion abelian group. So I can view this group as as a measurement of the failure of a Hasse principle. So for example, if this is trivial, if this set is trivial, has only one element, that means all the genus 1 curve with a given Jacobian variety, they all satisfy Hasse principle. If this set has a very large cardinality, or if this set has infinite cardinality, that means Hasse principle fail terribly. So that's one way to try to quantify the failure of Hasse principle. Well, so then the question would be, I mean, how badly, right, Hasse principle fail? So conjecturally, Tate-Shafarevich conjecture that this is actually finite. So in other words, the failure isn't really too bad. It's a sort of finite. There are only finitely many equivalence classes, at least within given if you fix the Jacobian variety. So the significance of this conjecture is that actually well, earlier I mentioned actually the local solvability is decidable. This implies, in fact, well, the question of whether a genus 1 curve has a global point also is also decidable. So this would imply, in other words, there is an algorithm to tell you whether a genus 1 curve has a rational point to decide existence, so C of Q, whether it's empty or not. So it tells if it's finite. Well, I mean, if we are given a genus one curve, so we can try to perform descent, and also, I mean, in the day you search for rational points. In the night you perform certain descent. No, but then if the group is finite, the algorithm will terminate in finite time. Oh, no, you don't. You just need to have the finiteness. I mean, the finiteness, well, in practice, it will always work because we believe it's finite. So the finiteness implies the algorithm will always terminate in finite time. Guaranteed. No, you don't need to know the bound, actually. When you well, so you do the descent. The finiteness will guarantee one day certain lower bound and upper bound will meet. Yeah, we can. Okay, so that's a definition of the group as well, at least as a set. You know, what are the elements inside? So I can even make this two torsion more explicit. So the two torsion, just to tie to this example, where example actually turns out to be one element. I mean, gives element, non-trivial element in the two torsion of theta-Rich group. So two torsion. So SHA of 2, so I can give a more concrete description. So these are precisely hyperelliptic covariant of P1. So pi degree 2, where Jacobian together with such a identification. So essentially, here the equivalence relation is even easier to describe. If you have two covariant, C1, C2. So the equivalent, if you have isomorphism, such a commutative diagram, then they are called, those two pairs, two maps will be called equivalent. So in terms of the equation here, I can even describe even more explicitly. If I have so continue for the two torsion. So if I use the equation y squared in g of x, remember g is of degree 4 polynomial. So you can actually change. Well, you can translate. You can change variable, right? You can change the variable, and you can take the. Let me write it this way. So in other words, you can change a variable in this way. Okay, you want to get a degree 4 polynomial, so you better multiply this fourth power, then maybe times also another constant square. So that would be the new g prime. So that's essentially telling you how to kind of identify two such hyperelliptic curve. And of course, you want the cubic resolvent to be the same as using here what I said here. So the cubic resolvent should be given. So it could be. So that's one way of concretely realize elements in the two torsion. Oh, sorry, actually, I mean, here I meant, well, actually, I meant this, I meant only, well, here, okay, what I'm doing here. So I meant C and this identification, so I only remember the curve. So what if I want to remember this cover itself? So this turns out to be, maybe I should have, yeah, if I want to remember this map, so this is what they call Seymour group. So I can define a two Seymour group of E as the set of such map, and also Jacobian up to the equivalence relation I defined here. So I should have defined the equivalence relation for the two Seymour group rather than for the SHA. So for SHA, for the Taylor-Chauvet group, I only care about the curve abstractly up to isomorphism, as long as they preserve this map. Clearly there is a map going from Seymour to SHA by just remembering the curve, forgetting the map. Forgetting the map. So by doing that, I end up with, so let me write as a fact, have the following exact sequence of finite abelian group. Namely, two Seymour group defined using, well, okay, again, always modular equivalence relation. Two torsion SHA. So the kernel turns out to be, so I was working with the base field K, so modular twice E of K. So those are all abelian group. Every element is killed by multiplication by 2. So they are all sort of vector space over F2, field of 2 elements. They are all finite dimensional. So it turns out the significance of Seymour group is that this set can be computed just by using this description by degree 4 polynomial modular suitable equivalence relation. So this one is actually, so the one in the middle, the term here, Seymour group is computable, where the other two terms in this exact sequence in some sense not computable in the sense you cannot tell. So given an element here, you cannot tell its image is 0 or not. So this term in the middle is something much more elementary, and it's managed to, for example, you can design algorithm to compute. So one example would be this. So this curve, this covering given by this genus 1 curve gives one element in the two Seymour group. And whether that genus 1 curve has a point, has a global point, depends on its image in the Taylor-Chauvet group is trivial or not. Okay, so now I'm ready to, haven't defined the Seymour group and Taylor-Chauvet group. I can state our main theorem here. So again, let me remind you, in the beginning I start with rational numbers, and then every construction here works for finite extension of rational numbers. and also finite extension of function field in one variable over finite fields. So here I'm gonna move to or more focus on the function field case. So the theorem. So this is joint with Zhiwei Yun. Well, still work in progress based on our previous joint work. So the result is following. So now assume K is a function field. So the theorem is the following. Suppose I know the two Seymour group has order 2. Actually, for simplicity, let me also assume. So remember E has an equation. So y squared being f of x. I have a cubic polynomial f of x being of the form. Okay, in the function field case, I'm going to assume the characteristic is not too bad. It's not 2 or 3. So let me not consider those pathological characteristic. Suppose this is irreducible. Again, this is it's not essential. I can state a result which does not need this irreducibility. In that case, if I assume this two Seymour group has order 2, so then the Taylor Shaffer group is finite. It's finite. Earlier I mentioned the significance of Taylor Shaffer group is the measures failure of local global principle. So here it's given a criterion to the finiteness of this group. And the criterion is in terms of the two Seymour group. As I mentioned, it's computable. So potentially the Taylor group can have very large cardinality. This result is seen. Suppose you do this computable. You work with the computable group, the two Seymour group. You have a way of detecting, proving finiteness of Xiang. So,
let me repeat the question. Prove this finite.
Yeah.
You have an effective answer.
Oh, for the order?
Yeah.
Well, I don't know. Actually, I don't know the answer. Depends in terms of what quantity. In the order, well, in the function field case, since this would imply the BSD conjecture, so whatever the BSD conjecture, the refined version, so okay, I don't know the answer to the effective of the bounding order. So let me remark. So here, so the prime 2 is not essential. You can replace 2 by any prime. So as long as you avoid the characteristic of my function field here, so 2 can be replaced by any prime L. And you can also do a stronger version, like you can even define 2 power, or 2 to nth power, Seymour group. So, and the same result will be true. So suppose that you have some easy, some weaker hypothesis, such as the high 2 power Seymour group has rank 1 plus a finite, a bounded term when n goes to infinity. So that also will give you the same consequence. again, replace 2 by any other prime different from the residual characteristic is also okay. So yeah, let me also mention, so here we are using some previous work. Previous work of Artin and Tate, where they prove that if you know the findings of Sha for the 2 primary part, then you know the findings for actually for all the for the full Sha. So Artin and Tate is already built in. And also, if you assume information from L function, so here we're not using analytical quantities such as L function from the elliptical curve, but if you do assume L function has order 1, then this was also known due to Ullmer using a version of Gross-Zagier in the function field case. So I think, yeah, there's also generalization due to, Zhiwei Yun and myself, and also Chonglin Qiu, under the hypothesis when the L function has rank 1. So it's a different type of result, but it's related. Right, so that's the so the result I want to present. So then I'm ready to return to my right, Artin Tate also tells us this would imply, maybe also for the Milan, to have the full BSD. So this implies BSD for E. So by the work of Artin Tate and Milan. Well, it's computable, I'm saying. Given any E, it's computable. Where this is, the Sha is considered to be not computable. So I want to explain why this result is in some sense useful in terms of solving definite equation for intersection of two quadrics. So let me now return to that question, to our earlier discussion on. So now let me, so part 3. So intersection of 2 quadric, higher dimension. Let's see in the dimension 2 case. Let's see. So I discussed in the one dimension case, the Hasse principle might fail, but the failure is finite, at least conjecturally, and in this case, it's provably actually. So this can be used to attack Hasse principle for the intersection of 2 quadrics in the dimension 2 case. So in this case, let me assume I have 2 quadratic form A1, A2. So I have 2 quadric defined by this equation where x has 6 variables. So I have point in P5. Need 5 variable. So 5 variable. P4. 2 equations. So suppose it's a smooth complete intersection. So that's the generic case. So let me recall again. So there is a so-called characteristic polynomial attached to the two quadrics introduced already by Wei. So you can look at this polynomial P given by this polynomial of degree, in this case 5 variables to degree 5. No, wait, how many variables? Oh yeah, right, degree 5 polynomial. So x is a1, or maybe called t, plus a2. So this polynomial of degree 5 measures, in some sense, give you invariance to attach to the two quadratic forms. So in this case, so let me state. So in this case, I can compute the canonic sheaf for this intersection, so defined by two equations. It's a two-dimension varieties. It's given by O of. So suppose you have something in Pn, then I have 4 minus 1 plus the total degree, 2 plus 2, so I get 4. So actually, it's O of -1. So this is one example of so-called del Pezzo surface of degree 4. Where the degree means the self-intersection of the canonic sheaf. So right, so in this case, let me state a result regarding the Hasse principle. So it's known in general, the Hasse principle also fails for del Pezzo surface over, in degree 4. But you can prove under a very general, quite a general, for quite a general classes of del Pezzo surface in degree 4, Hasse principle actually holds, provided you assume. So the theorem I'm going to state is due to Wittenberg, where he did for number fields. For number field, so K 0 characteristic. So the theorem is the following. Suppose the characteristic polynomial P, the characteristic polynomial I introduced, the degree 5 polynomial, suppose it's irreducible. So assume. So again, you need some hypothesis because it's known in general this Hasse principle is not true. Irreducible. Let's say has Galois group, maximal Galois group, being S5 or A5, so almost maximal. Then he needs two more hypotheses. He needs to assume. So one is actually finiteness of Shah. So one is Shah is finite. Well, for all the elliptical curves involved in his argument, so he's going to perform an argument which involves elliptical genus 1 curve. So he needs to use Hasse principle for those genus 1 curve. So he needs finiteness of Shah. Secondly, he needs some generalization of twin prime conjecture, so-called Shinzo's hypothesis. So this is a generalization of Dirichlet result on the infinite many primes in any given congruence class. So we assume those two sort of conjectures. And this condition, then Hasse principle holds for del Pezzo of degree 4. So those interesting in two quadrics. So I want to mention that. So okay, the finiteness of Shah. So it's expected in the case of the piezo surface, floor mining obstruction is the unique obstruction. I mean, it's conjecturally. That's the only obstruction. So in this case, under this Galois group being S5 or A5, yeah, the floor mining obstruction vanishes. Well, here he's assuming like the maximal generality. So shell of all elliptic curve. Yeah, for a class of elliptic curves to be finite.
For every elliptic curve?
Let's say every elliptic curve. Yeah. Although he doesn't need that strong. Actually, as I'm going to say, the reason our result is useful is precisely what we proved is sufficient for this hypothesis. So I'm going to describe very quickly. So why this is? It's actually a very natural idea because, well, given an intersection of two quadrics in P4, this surface has a natural family of genus 1 curve. Namely, so here I have the surface. Let's say this is P4. So clearly I can impose a linear equation, right? So that would give me an intersection of two quadrics in P3 in a hyperplane. So if you take a hyperplane section, you actually get an intersection of two quadrics in P3. That is actually a genus 1 curve, which we talk about. So one example was given here. So you get one such. So in other words, you get a fibration. So you have So the idea is to do a fibration over P1 where all the fibers, at least generally, they are genus 1 curve. So those are genus 1 curve. So he used Shinzo's hypothesis to prove that actually you can, by assuming local solvability for the surface, you can prove existence of at least many fibers. They also satisfy local solvability. Therefore, they define elements in the 2 Seymour group. Actually, maybe in this case even 4 Seymour groups. But then he even argued more. He can arrange. He can choose certain fiber, and he can arrange in such a way that those genus 1 curve, their associated elliptical curve, has a Seymour group precise of order 2. So then he applied the findings of Shah. He can show that actually such order 2 in order 2 case, I should have mentioned earlier. Here I have this exact sequence. If this has order 2, then since we expect this group to be square order, so if you know this is finite, it has to be square order, so that we force, in the case under this hypothesis of my result, our result here, two parts of Shah will be trivial, which means this genus 1 curve actually has 0 class in the theta-Javashi group. Therefore, it has a global point. So that's how he applied this and how he assumes, why he needs to assume this findings of Shah. But in short, his assumption precisely needs the result we proved. Okay, so now if we apply our result, one has to do the same argument for function field, but I feel it's, people have to check, but it's expected to work. What is, in other words, the theorem can actually, can remove this hypothesis. Okay, that still leaves the Shinzo's hypothesis, which feel very, as far as I know, even in the function field case. Wait, you mean the?
What is that?
So yeah, I was planning to state what is this hypothesis. So basically it says if you have a bunch of polynomials, so I'm stating the following version. Suppose I have finitely many polynomials, so in finite field, P, say 2 variable. Although it's really 1 variable with coefficient in the room of integers of the function field, so irreducible. So assume it's reducible, then, okay, well, this is conjecture, so Shinzo, right? Hypothesis says, then you can find infinitely many value of fi belongs to one variable polynomial ring such that all those values such that fi p fi of t, so the output will be polynomial in one variable, so they're actually irreducible. So they're giving you prime ideas. So that's this hypothesis, kind of. Oh no, right. So there's no I, just infinite many polynomial which you plug in.
So finally many fi, right?
Yeah, this family is finally many. So from one, finally many two variable polynomial. So, okay, so again, I don't know how to prove this. So my knowledge is that people haven't proved this hypothesis, even in the function of the case. So that's a bit disappointing because I'm still stating a conditional result. I'm only removing one of the two hypotheses. So in the end, let me, well, I can move to more equations, which can be actually done in the same. So I wanted to mention this sort of fibration when doing a two descent argument was already known before Wittenberg, used by Swinnerton-Dyer in many cases. And Swinnerton-Dyer actually did the same, well, use kind of similar ideas, but without have to assume Shinzo's hypothesis. He actually managed to prove some results which only assume fineness of Shah. So I'm gonna very quickly tell you there are cases where you can avoid Shinzo's hypothesis. Therefore, our result can actually be applied to give unconditional result. But the reason I decided to state this result was because it's much more general. It looks like, at least the conditions on the Galois group is easy to state. Where what I'm gonna state next is other type of application to other type of equations. So this is due to, well, it's based on result of the fibration and descent method due to Harpaz and Squirrel Bogatov, where they prove results like for the following two type of varieties. One is the Kummer surface attached to so two cases. One is for abelian surface being a product of two elliptic curve. And so the torsor is attached to such a abelian variety. So in this case, you can write down equation like y squared. So this gives you equation like z squared in the affine equation, g1, g2, y, where g1, g2 have degree 4. So it's exactly one of the cases I introduced earlier. So this, you have two sort of genus 1 curve attached to those two degree 4 polynomials. And then you produce the Kummer construction, namely divided by involution of order 2. Then you kind of resolve the singularity. So I'm writing down the affine equation. So this is one type. But okay, he needs to assume, their result needs to assume Tetris average group is finite, and also there's some conditions on the elliptic curve. It's not like they have a result for all elliptic curves. So that's why I don't have actually a simple statement as that one. So you have to assume those two elliptical curves satisfy certain disjointness of bad reduction and more conditions. So it's a bit hard for me to state a complete statement. The second one is for any, again, for the Jacobian of a genus 2 curve. Genus 2 curve. So in this case, the Kummer surface actually attached to, well, again, you have to take a tosser under the Jacobian variety, then you produce the Kummer construction. But I can write down the equation in this case for the surface. So X. So this case is actually defined by intersection of 3 quadrics. So it looks like AI xi square in 0. bi xi square 0 ci xi square 0 inside P5. So this case, they can, in both cases, they only have to assume functions of Xia. In a sense, the same type of result we could prove, but not without assuming Shinzo's hypothesis. So I mean, again, I'm not writing down the exact statement, I feel, because there are some local conditions for the reduction type of those abelian varieties, and also they have some further conditions on to simplify matters, to do this sort of 2 descent argument. But it seems to be helpful to kind of to improve and to get a more general result. Yeah, since mathematicians barely work with a number bigger than 3, so I'm happy to stop here for the intersection with 3 quadrics. And thank you.
Any question?
Dimension 3. Oh no, actually the higher the dimension, well, it depends on how many number of quadrics. So for 2 quadrics, this is stronger. Actually, this is enough to imply, I mean, the Hasse principle for intersection of 3 quadrics. Well, sorry, I mean, no, wait, you mean dimension 3, right? Yeah, dimension 3 case. But actually, in the function field case, this is known already by different methods. In the number field case, I think that people know the Hasse principle when the dimension is maybe bigger than 5 or high enough. So the dimension 2 case is kind of the critical case. In the function field case, dimension 3 or higher were proved by Zhiwei Yun, actually, in the function field case. So it's proved for dimension 3. So in some sense, what's left is the dimension 2 case to be understood for intersection of 2 quadrics. What do you mean? Yes, Hasse principle is known for, see, the number field case for dimension, I mean, if you look at intersection of 2 quadrics, for dimension 5 or higher, in the number field case, it's known. I think Hithborough proved for dimension 5 case, maybe higher was even known before. For the function field case, it's known starting from dimension 3, which was Chris's question in dimension 3 case. So in other words, I mean, what's remaining is really the dimension 2 case being the most challenging case. So the higher the dimension is, actually the easier the I'm talking about the intersection of 2 quadrics. Yeah.
What about 1 quadric, 1 cube?
I don't think that is known. In fact, one interesting question would be, can one run this fibration method to cubic surface? Because you have a pencil of genus 1 curve defined by cubic equation. So in that case, you have to consider 3 Seymour group. But then this argument of Wittenberg, I haven't seen anybody who has done for the sort of cubic surface. But I think it is an interesting question. Can one do the same argument, even if you have to assume this type of hypothesis? But to answer your question, I think the answer is we don't know. I mean, people haven't understood. Yeah, after the talk, yes.